So now this will be the third lecture given by J Stebe. It will be on directed assembly at fluid interfaces.
Okay, so it's great that I get to speak after Oleg because I snuck some material related to his work into the last lecture because his work is very inspiring but it's also high pressure to speak after that man. So we'll see what I can do. So Oleg referred already to the ideas about why do we want to look at colloidal assembly. And I drew a distinction between order KT interactions and stronger interactions. And so what I found most intriguing, I think, is in interacting as a chemical engineer with physicists who work on the colloidal community, who work in the colloidal community, is the way in which they think about colloids when they're thermal as model atoms or molecules. So they know full well that, so for example, if you were thinking about interatomic interactions, you would have some interaction potential, and the molecules are thermal, and they can be guided into forming structures by manipulating those potentials. And since colloids are thermal as well, they allow people to think very often about model potential fields, model interactions, and what structures emerge. And so for situations in which the colloids are thermal, in which they are interacting with order KT interactions, they are often used to inspire some relationship that's going to transcend scale. That you think about interaction potentials that are happening on the colloidal scale, and you think about what analogies might exist at other scales in systems that can be thermal and find some interesting equilibrium. So that's really the underlying concept of self-assembly. And so just as in self-assembly in biology, for example, you can get increasingly sophisticated structures by playing with the structure of the molecules themselves, there are entire fields of colloidal science that are moving from colloidal atoms toward colloidal molecules, where they're making, for example, means of manufacturing complex structure colloidal molecules that will have, say, one particle and two lobe particles and be analogs to, for example, a water molecule, etc., are developing. And so there's this entire field, which I'm not talking about today, but I wanted to make you aware. Okay. I'm more talking about the field of directed assembly. So in directed assembly, it's this idea, for example, of electrophoresis. You say to some particle, I'm going to apply some external field, and I'm going to tell you, whoosh, go over there. And Oleg showed beautiful examples of colloids obeying him, going where he told them to go. Okay? And so I'm going to spend some time talking about what happens with particles when they're just trapped at isotropic fluid interfaces. So we'll come back to this example several times, but these are just epoxy resin cylindrical microparticles at an air-water interface. They're about 20-odd microns long, about 7 to 10 microns in diameter, and they're sitting at an air-water interface. And you can see they've already interacted so that they're somehow oriented with respect to each other. And if we just take a movie of their interaction on the interface, we'll see that they're not thermal. Any jostling you see is because of uncontrolled vibrations in my lab, not because of some thermal effect. But you saw they come together with tremendous fidelity, end to end. And so the energies of interactions are many thousands of kBt. And so this is much more akin to the concept of there being some external field. But in fact, it's not an external field. It's just a soft object. It's a hard object, the cylinder, placed in a soft host, the fluid interface, and making a distortion. That distortion carries energy. That energy drives assembly. So I want to guide us through first just thinking about these sorts of events on planar interfaces, and then the next hour will be curvature. Okay. And I didn't do a responsible literature review, but I've snuck a movie from Valeria Garvin at the end of this talk of something she recently published in JFM. And this is just an example of an excerpt of a nearly responsible, literature review in the subject. There are many, many, many excellent papers in this domain, and so in no ways have I done an exhaustive review. But I'll leave this, for example, and some representative papers in a folder for all of you, but in no way is it exhaustive. This work is the ideas of looking at particles at fluid interfaces. There's pioneering work by Kralchevsky, Dietrich's group does beautiful work, et cetera, et cetera, et cetera. The Cheerios effect. Okay. Right. So just some ideas to sort of get us started. So one idea that pervades work for any time we have a solid in contact with a liquid and in contact with a vapor, or a solid, one liquid, and another liquid, is the concept that the three-phase contact line can come to equilibrium. And so that concept that the vapor-solid interface and the liquid-solid interface each cost energy, as does the liquid-vapor interface by interfacial tension. And so there's a balance of energies at a contact line, which defines an equilibrium contact angle. So that's one concept. And so this equation, the Young-Dupré equation, defines this angle at equilibrium in terms of the relevant surface energies. And then there's another idea that just flies in the face of this, which is that we don't come to equilibrium. That contact line sits there, and there's the liquid, vapor, and solid. And the liquid contact line can't undergo some thermal search for what's happening around it, because it's trapped. It's trapped on a rough site or in an energetic trapping site, in which case you have some sort of contact line pinning. And the fluid interface would try to minimize its area, yeah? But the contact line will not necessarily be at equilibrium. And these concepts of contact line pinning, really T.D. Blake and his collaborators over the course of their career really focused on this idea, and there's a very beautiful literature developed around this concept of kinetic trapping on patchy sites and then hopping from site to site. And more recently, it's been shown to play a tremendously important role for colloids at fluid interfaces. And so we can discuss the different limits. I can talk to you about an equilibrium contact line, and I can talk to you about pinned contact lines. Okay? So why? Let me just give as a preamble. If I put a particle on a fluid interface and I have an equilibrium contact line, then if it's a perfectly smooth, perfect sphere, it can come to some location on the interface, keeping the interface around it planar, and obey its equilibrium contact angle. My cylinder on a fluid interface, it couldn't do that, even with an equilibrium contact angle. If it had some attractive wetting on the side, then that was going to come up and give it some angle, yeah, some acute angle. But it couldn't remain planar and stay at the interface. So the curvature along the sides requires something else. Okay. The only time I can stay perfectly planar is if I have a 90-degree contact angle. The energies of interaction, this is just by way of motivation, are the fact that these particles present at the interface, if they deform the interface by wetting conditions, they make some excess area. That excess area multiplied by interfacial tension is an energy field. And so I just want to go over some preambles to how do we get started to think about these energy fields. So the first was what happens at the boundary, the contact line. The next is what governs the interface shape. And so if I'm looking at the shape of a fluid interface, the fluid interface wants to minimize its area. And so if you set up to understand that you arrive at the Young-Laplace equation, that the jump in pressures across the interface is balanced by the mean curvature of the interface times the interfacial tension. And if I'm looking at a system which is planar, or with small disturbances, at least along the planar interface, because I have this reference plane, the pressure jump across the interface is going to be 0, and the mean curvature will be 0. And in the limit of small slopes, the shape of the interface just obeys the Laplacian. So right away you see that we've taken this problem and we've moved it into a system where if I'm looking at small deformations, the language of electrostatics is going to be brought into play. The distortion of the interface, the height of the interface over some reference plane, is obeying the Laplacian, and so the distortion fields and their interactions are often discussed in the language of electrostatics. Okay. So just the concepts also of curvature of an interface. We can define principal curvatures along the surface with principal radii along the principal axes R1, R2, and the curvatures C1 and C2. And in the limit of weak slopes, I can just break that curvature into two pieces. The mean curvature would characterize a bowl-like distortion, and the difference in principal curvatures characterizes a satellite distortion. So if I wanted to talk about, for example, a curved fluid interface in the limit of small slopes that was some distortion above a reference plane, I could describe it in terms of this saddle piece, which is weighted by the difference in principal curvatures, called the deviatoric curvature, and this bowl piece, which is characterized by the mean curvature. Okay, so now put a particle at a planar interface. So why do particles get stuck at planar interfaces? And the whole idea is this, is that air-water interfacial tension, for example, let's take that as an example, like when you make hot chocolate. I referred to it yesterday, but again, you make hot chocolate and you sprinkle the powder in, and it stays at the interface. And the reason it stays there is because the ability of the particle, if it started out underwater, and then it ended up punching a hole in the interface, that it reduces the area of the interface by this circle that it's created in the interface. So in other words, here, there's some circle of liquid vapor interface that's been eliminated. And that hole in the interface lowers the system's energy considerably. And so we can do this, we can say, well, just let's look at the state 1 is an intact interface with a particle underwater. State 2 is a particle adsorbed on the interface, and you can calculate the change in area of that system, and then calculate, multiply it by interfacial tension, and get the change in energy between being under liquid and on the interface is just given by an argument in terms of the liquid vapor interfacial tension. That would be the area of the hole made by a particle if it were at its 90-degree contact angle. But if its contact angle is not 90 degrees, there's a correction because of its wetting energies. But this is really the whole story about why things accumulate at fluid interfaces to begin with. So if I think about liquid vapor interfacial tensions, like air-water is 72 millinewton per meter. That's 18 kT per square nanometer. So even a nanometric object in the interface is going to have considerable trapping energies. Okay. And I'm looking at micrometer scale objects, which can have trapping energies many, many orders of magnitude larger. Yes? Okay, so that's why particles are at the interface to begin with. They become trapped there. And yeah, so for microparticles, we're on 10 to the 6th or 10 to the 7th kT. So that's the idea of when people talk about particles being trapped at fluid interfaces, it's that simple fact. Punching a hole lowers the area, lowers the energy. Then we could ask ourselves, well, what about a small particle sitting on a fluid interface and it has a pinned contact line? So, so imagine instead of having like a nice belt, it has some pinned contact line that's very irregular. They're Apache sites, right? And so this irregular contact line is forming whatever angle it comes to, apparently at larger scales, and it's influenced by this zigzag nature of its contact line. And so we can decompose this into its Fourier modes. And you can say corresponding to each Fourier mode, there could be a distortion in the interface. So for example, if I were a heavy particle, the particle could pull down and the interface would pull up, right? And that would be the strength of this monopolar distortion here. Or if I, for some reason, were heavier on one side than I were on the other, I could tilt and the interface could balance that. Okay? But in most of the systems we're looking at, the weights and any distribution of body forces on these objects are negligible. And so, the leading order mode, the logarithmic term is 0. The dipolar terms are 0. And the first survivor is this quadrupolar mode. Okay. So this ends up being a powerful statement, because if this is the first surviving term among a bunch of decaying terms, everybody decays with distance from a particle. So I don't need any of the growing terms. I only have decaying terms. So the quadrupole is the first surviving mode. And so it defines the longest range interaction between every object on the interface. And this is arbitrary. Just have messy contact lines form quadrupoles. Okay. So here just is showing graphically, and here just baby calculus. If my particle, here we show, for example, like a buoyant particle, it could pull up, but tangent to the interface, the surface tension is going to pull down. And so absent any buoyancy or weight, surface tension is going to annihilate that distortion. Boom, pull us back into plane. So we don't have that one. Similarly, the dipole, if I tried to make a distortion high on one side and low on the other, the surface tension will pull on that and twist it out if I don't have some body torque. Okay. And so the first mode that can support itself, and all higher order modes, are cosine 2 phi and higher. Okay. So if I think about the excess area on the interface owing to this particle's presence, first I would say the particle punches a hole in the interface, which is modulated by the liquid solid and liquid vapor energies. That's this term, very much like the Paransky term, but now it's whatever contact angle it found. And then there's a self-energy term that's about its distortion, its first surviving mode. And then there would be higher order modes. Okay, so we're just paying attention to the first mode. Okay. So what if my particles aren't simple in shape? They're not just spheres. In which case, shape starts to matter a lot. So here, for example, is an interferometric image around a cylindrical microparticle. And we can see it doesn't look like cosine 2 phi. I mean, actually, far away it does. Very, very far away from that particle. 40 radii away from the particle. We can say the distortion in the height of the interface looks just like cosine 2 phi. Closer in, we still have that. But 10 radii from contact, we can already see pronounced peakiness here at the ends, much larger distortions at the ends than we're seeing along the sides. And so this was a shape with quadrupolar symmetry, but already you can see details of shape are mattering. Far away, everybody obeys cosine 2 phi. Closer in, we're seeing that this object is elongated. And if we went closer in still, things like corners, edges, and roughness are going to be playing a role. And so these are just a bunch of objects that have quadrupolar symmetry. This is let's see, a poppy seed, our cylinder, a water lily leaf beetle, and the movie won't play, but if you can find this online, it's the most adorable movie ever. I'll tell you about it where we study the phenomena. This is an ellipse by J.C. Ludet. There's a paper strip that curled up, but you can see this quadrupolar symmetry far from the object, and then details closer in. So I'm going to talk a lot about the cylinder because it's a nice example of something that had these oh, and by the way, if we deliberately put in a tri-lobed object, like we made a little Y-shaped thing, and then we bent it so it came up out of the interface. So we were saying, okay, good, we'll make a hexapole. In the far field, it was a quadrupole because that was the longest range. So whatever funny roughness on here could excite that mode, that's what we saw far away. Closer in, we saw what it was we had imposed. Okay. So if we look at the cylinder, we can see, for example, this is a simulation using surface evolver, assuming equilibrium wetting on this object. So there might have been contact line pinning, but this thing was trying to tend towards some equilibrium. We used the equilibrium to guide our thinking. And we can see very, very strong distortions very close to the ends. If we look in the regions of corners, which I'll zoom into later on more, they're real hot spots. But qualitatively, we see this rise on the ends, this downward deflection of the bowl on the sides, and the rise on the ends again. And here is a PDMS negative of the interface taken by environmental SEM, and you see this distortion along the ends as rise and the downward deflection along the sides. Okay. So if we look at this, from the top view, you could see these are isoheight contours around the cylinder. This is around a quadrupole in elliptical coordinates. So in fact, there was a very beautiful piece of work where people had simulated in detail an ellipsoid and the shape of the interface around it. And the complete set that they used to do that was an expansion in elliptical coordinates, a multipole expansion in elliptical coordinates. And it converged very quickly because they used that coordinate system. And so we were inspired by that. We just said, what does this mode look like in comparison to the distortion that the cylinder's making? And in fact, within a few radii of contact, these two agree quite well. And so the basic idea for an elongated object is far away, this distorts to be, this just decays to be a polar quadrupole. Closer in, the elongated nature of the object matters. And closer in still, the strong distortion in the region of the corners matters. And so you could see that it's if you're walking through a foggy night and you see your friend. Far away you see an object. Closer in you see that that person's tall. Closer still you might be able to distinguish their features. Okay. Other distortions we could set up. So for example, one question is, what does roughness do? So we made particles that were wavy particles to have model roughness. And the idea of roughness here is that we're going to set up some undulation, which is a fast frequency undulation compared to the length scale of the object. And so just solutions for the Laplacian for a wavy wall would tell you that they'll decay over distances comparable to the wavelength in the interface. And so the frequency of the roughness, faster roughness, sets up nearer scale interactions. And they can be attractive or repulsive when we get to pair interactions. This guy had a little bit of a bent back on purpose so that he'd make rise, and fall going around the object. And if we look at it, here's interferometry. In the far field, we can see that quadrupolar mode. In the closer up, we see the effects of model roughness. Okay, so I think the main idea here is that trapping is a big deal. If you have an anisotropic shape, you're going to distort the interface around you. But even more so, if you have a noisy contact line, which is the norm, you're going to be distorting the interface around you. So even apparently isotropic objects, like spheres, have leading order mode distortions which are quadrupolar. And so they're not isotropic. They're going to have interactions that are quadrupolar in the far field. Okay. So what about if we're sitting on a curved interface? So now let's think about a saddle-shaped surface, because it ends up being the interesting case. So if we think about a saddle-shaped surface, then we can, as I mentioned earlier, we can describe the shape of the host interface. If we think about sitting just at a point on the interface and describing the shape of the interface around a center where that should be coming, R should be from the base of the well, that we can expand this to be locally a saddle, where delta C, this difference in curvatures, is the difference in principal curvatures of the interface. In this case, then, I can say, if I had that particle sit on the interface, how does it change the area of the interface now? And so if you think about this, think about to sit on the interface in the plane of the particle punching a hole in the interface, and you think about a saddle. You say, what if I were going to punch a hole in like a cowboy saddle? So you have like a cookie punch, and the area that you would punch out would be larger than a plane. And then if you had like a little child's saddle, and you were very cruel, you could punch a hole in the child's saddle. And the patch of leather you would pull out would be, because that has much tighter curvatures, you would have an even larger area. So we could expect some contribution potentially from the hole that you're going to make in the saddle shape. But furthermore, then if the particle pulls the fluid interface up to its contact line, and then we have a quadrupolar mode around that, pulling the interface up to the contact line, let's think about a saddle. It's going up in front of me, and I'm pulling down. And then it's going down beside me, and I'm pulling up. And then the distortion I make to try to bring that to my contact line is going to be larger, the tighter is the saddle as well. Okay. Then on top of that, I'm putting in my quadrupolar undulation. Okay. So if I go about solving that problem, I can, first let's think about it's equivalent to solving for a disk except for the little wetting energy parts about which I don't care so much right now. We could calculate the hole in the interface and the distortion made around the object by just solving first a boundary value problem where we say that at the contact line, please obey the quadrupolar mode, and far away, decay to the host. and here's the host shape, and these are the disturbances made by the object, which I could break into two parts: the induced one that fights the hole in the interface, and the distortion that was brought by the particle itself because of its contact line. And if I calculate up those areas, I'm going to have the area of the hole, the area induced to create the distortion around me, and then a cross term between the induced and the object itself. And if I go about calculating all of these things, the interesting thing is that everything we had intuitively about the hole in the interface and the distortion it makes around it, they're equal and opposite. So that's not the story. The story really comes from the induced distortion made by the object interacting with the quadrupolar mode brought by the object. And that brings us an excess energy that's related to the curvature of the interface. So when we're all done with that, and we also had our self-energy that came from our quadrupolar mode. So if I go back and I look at the energies, they just turn out to be the energy I had when I was alone on a planar interface, and an extra term because of the interface curvature. Okay? So curvature changes are trapping energy. So those are for isolated objects. But what about for pairs of objects? So I already showed you this movie, so I won't show it again. But here I have a cylindrical particle, and that particle is sitting in the interface, and it's made a distortion field around it. Far away, all I see is that it's quadrupolar. Right? Far away from this object, all I see is that it's got some quadrupolar distortion. And in the near field, I see details, and those details end up mattering a lot and are going to end up influencing the structures that we can form. But first, in the far field, particle 1 sees particle 2 in the far field this way. Particle 2 changes the shape of the interface nearby. And so particle 1 says, first of all, particle 2 changes the height. But this guy can't make a monopole, so he just says, I'll just rise with that change in height. This neighbor changes nearby to this one, changes the slope. And the particle says, I don't make dipoles. I'll just rotate to orient in that slope. Then this particle also makes some local curvature field. And because this is a solution to the Laplacian, this is just a little saddle shape curvature that it makes. And this particle is going to interact with that curvature field. Okay? So particles interact because I see your curvature field that you made near me. Okay. So this is just summarizing that idea. I change my height, I tilt, and then I react to the curvature. And so the way I react to the curvature is I'm solving this problem for a pinned contact line. I've pinned my contact line to make some quadrupolar mode. Okay, this is the height I'm making above my reference plane, which is now changed. I changed my height, I tilt. And now I still have my quadrupolar mode. And this is just like the problem I just solved. That my particle is now sitting in a curved surface. That curvature happens to be coming from my neighbor. I go about and I solve the boundary value problem to find the distortion that's made, the host interface. The host interface shape is coming from my neighbor. And then I bring a quadrupolar distortion, and I make some induced disturbance to be able to enforce my contact line at that location. And now we just go about calculating up the excess energies. And the excess energies tell me that my particles interact this way. And this is completely analogous to the problem that we did for the curvature field previously, where the curvature field that was coming from the particle could be written this way. Okay. So particle 1 moves in the curvature field of particle 2. Particle 2 moves in the curvature field of particle 1, so you put a factor of 2 in front. And this is the pair interaction energy for any two particles interacting in the far field. And it's a very powerful result. It was first derived by Stamu. He used a slightly different mode. We're using the method of reflections here. But it has some very powerful concepts. It says that particles are going to attract along their line of centers, provided that this argument is positive. Okay? And so we think of it this way. Particle 2 has made a saddle deformation here, and I'm a quadrupolar distortion. I have rise, fall, and fall. And I'm sitting now in a saddle-shaped surface. Let's suppose the saddle rise goes this way and fall goes that way. I want to minimize the area of the interface. I have a local torque. Put my rise along the rise axis. And so this alignment along that rise axis, along the curvature that's being made by my neighbor, that's what this is. It's telling me to align my quadrupolar rise with that of my neighbor. Okay. But in fact, it's more general than that. Any distortion will do, any mirror symmetric. So if this is quadrupolar rise, and fall, that's attractive, that's attractive, that's attractive. Nothing's selective. It's just as long as we're mirror symmetric, we will be attractive. This argument will be one and will be attractive. And so this is the idea for why do pairs of particles interact attractively. And so if we compare the method of reflections to a more exact solution in bipolar coordinates, the two energies agree. So saying if you believe the boundary value problem and you solve it different ways, we're okay. Okay. So to test this, we've made these cylindrical microparticles. And so these are experiments from some time ago. These are just SU8 microparticles made from a photoresist. And so this is a very standard technique to make things like microfluidics devices or et cetera. It's just, this is an epoxy resin that you spin coat into a film, and then you can illuminate it with a UV mask, and everything under the mask gets cross-linked. And then you put it through developing steps, and then you can sonicate and release all of these little cylinders. So you've seen this movie. This is what happens when they're first interacting end-to-end. And here, they start out side to side. They have a near-field torque. So that's all from the energies in the fluid interface. And if we look at such interaction energies from various distances apart, when they're still in the far field, we can compare it to a power law. And we can just say, well, how does my separation distance up to time to contact vary? And we look at it for different aspect ratio microparticles, and we can see that they vary in the far field with a power law that goes to the 1/6, which you can recover just by equating our interaction force, which is just the derivative of our interaction energy, which goes as r to the -5th, to the viscous drag, which goes as dr dt. And so we can predict that. We can confirm that we've obeyed the predictions by STAMU in the far field. And the dissipation over an interaction event, a typical dissipation, is a 10 to the 5th kT. So as I said, these are not at all thermal, but these are for objects that are about 10 microns in diameter, and they scale with length scale squared, right? So we could conceivably still, down at 1 micron, we'll have thousands. At 0.1 micron, we'll have, should be able to do about tens, right? So at hundreds of nanometers, we should still have quite large interactions. So then trying to go further, we've captured the far field, but what about that near field torque? And I mentioned that we had this strong resemblance between iso height contours for the object and for a quadrupole in elliptical coordinates. And if we just take the quadrupole in elliptical coordinates and calculate its interaction energies, then they're going to capture this near field torque. And it's quite simple. The distortion near the ends here is much more concentrated than along these elongated sides. And so getting these two to overlap lowers the energy of the interface a lot more. And so this is just the experiment you saw previously slowed down, and that's just an Euler scheme stepping through, and that captures that torque. But then the things stay cemented end to end, and here's what elliptical quadrupoles do. So this isn't the whole story. So if we want to understand the whole story, and let me just show you this preference for end to end is quite robust. This is an experiment in which we compress these particles in a monolayer of surfactant that had been very, very densely packed. And then we put something in the subphase that melted the surfactant away. And then when these particles became freed up, their preference for end-to-end assembly was crazy. They just collect each other always by ends. They very much prefer the ends. Okay. All right. So the answer there lies in the details of the capillary bridge between the particles and the very strong distortion that we get near sharp edges. And so we can calculate, just using just calculating the shape of the fluid interface quasi-statically, and saying, what if my particles are near contact, aligned end to end, or if we rotated them to rotate them side to side? What's the energy at each step? And so what we find is this. We find that, that the energy for end-to-end alignment is a strong minimum, and there's an energy barrier at which you would go to side to side. But we also find here that if you put in more detail, that's not a parabola. It's nearly linear at this end-to-end alignment. So it's not a nice, flexible bond. We don't perturb nicely about it. If we took derivatives of this with respect to angle, we would predict a yield torque. We would say, let's suppose, for example, because the derivative of the line is going to give us a constant, right? And so it gives us some number up here. And so the idea would be, if I thought about trying to snap this bond, and I would have to apply some torque, higher, 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 finally I would snap. But once I snapped, there's nothing else in equilibrium with me. Okay. And so these should break by snapping. So we ran either successful experiments to show that these were rigid, or failed experiments to snap the chain. Okay. So that's a magnet that's cylindrical, that's been integrated into this little object, and we're just whipping it around at some insane rate. I don't remember how much this is slowed down. But our yield torque should be 10 to the 7th kT, and we couldn't get there in this experiment. So this thing was just whipping around and just staying rigid as it went. So the mechanics of things are not nice and flexible. And that's in marked contrast to ellipsoidal microparticles of the same size scale. So ellipsoidal microparticles come together if they have weak surface charge to make these nice wormy structures. And these wormy structures are nice and wormy because of the details of the wetting. That's at air-water interfaces also. The details of their shape and the wetting of their bridges between them. So I've moved it. So the shape, in that case, if we look at the energy landscape, we take ellipsoids side to side, and you gently rock them and say, what are the details of the capillary bridges between them? And here, side to side is highly favored. And the well is a nice parabola. And that nice parabola is going to give you a nice, in the energy landscape, close to equilibrium. And that's going to give you a nice elastic constant for flexible chains. Okay? So the details of the energy of the wetting as a function of configuration can give you some insights into the structures that can form. So these things are very attractive. And the question is, can we impart some repulsion to counter this attraction? And in a way, it's a problem, because we come very close to contact. As smooth as my cylinders are, I couldn't tell from our techniques to see what was between them. And then we're looking at 10 to the 6th to 10 to the 7th kT of interaction in some cases. These are very strong interaction energies. And so the way to counter is, in fact, to use the same weapon, to use capillarity, because these energies are so strong. And the concept here was just to use roughness. And if you go back in the literature, there were two different groups that were working on capillary effects sort of classically for heavy objects. And one group, because it's really important just as an aside, people were looking at small, heavy colloids trapped at fluid interfaces and their capillary interactions in the limit where the particles were large enough that they could distort the interface, because the heavy objects trapped at the interface would attract each other, and then they could skin those particles up. And it's used in recovery of ores for mining. It's called froth-based recovery techniques. It's quite classical. So that group had said, we wouldn't expect any interactions between particles if the particles aren't heavy, because they were relying on the monopole. And this paper was a reply to that. It was by someone named Lukausen, who did a lot of work with surfactancy, and he just did this one thought problem about, you could anticipate interactions between particles even if they're not heavy. But his anticipation was, what if they had wavy walls? So let's think about the particles as being abstracted as one wavy wall and another wavy wall. And this one has some very slow mode of some wave. That's its roughness. And this one has a faster mode. Okay. then if these particles were placed on an interface adjacent to each other, and we paid attention to the area in between them, we would see that, first of all, the distortions from this one decay over distances to its compared to its wavelength, this one over distances comparable to its wavelength. When those distortions overlapped, objects with identical amplitudes and frequencies and that are in phase attract. Else you're repulsive. So the idea there is that if you pushed a fluid interface pinned on this wavy line close to an interface pinned on that one, when you get close together, you're going to have regions of rise being pushed like a snowplow into regions of fall, and it stretches the interface. It costs energy. So we made the wavy particles, and here's just some simulations of here matching undulations with interface in between them, and this one can slide to that one, just slide the interface away. And here, mismatching wavelength, where you can see the hill from this one coming into some trough in that one, and that's a strong stretching of the interface, if the contact lines remained pinned. So I mentioned that we made these wavy particles, and here is a movie of two matching contact lines. And so in the far field, they're interacting like quadrupoles. And when they get closer, the extra undulation, because of their end, snaps them together with an extra energy. This one has a slow, it happens to be short this way, that's not the point. This one has a slow wavelength, think like Ruffles potato chips, slow undulations, or sun chips maybe. And then this one has really fast, it's a fast corrugation. And so these two, they attract in the far field. And then if we were to zoom in, they have excess interface between them. Okay. And these bonds are in fact elastic, so the mechanics is also different, that they're quite bouncy. And so if you look at their energy minimum as a function of separation distance, they're quite stiff on, they really resist coming closer together and are quite much easier to stretch apart. So they're these nice bouncy bonds as opposed to the rigid ones that we saw previously. Okay. So I've gone quickly. That's okay. We'll discuss. I have talked to you only about situations in which we have particles that are sitting on quiescent interfaces, and the particles make a distortion. So just to recap where we are, and then I'll say one or two words about recent work from others, and then I might pop a little bit to lecture 4 where I have a lot to cover. We said you put a particle on a fluid interface, it punches a hole. But if it has a shape that's not spherical, or if it has a pin contact line, it's going to make excess area in the interface around it. It still will remain trapped because the area that it made by punching the hole is typically much larger than the distortion it makes. Okay. So particles get trapped, and they can distort the space around them. And because they can distort the space around them, and it's a very slow decaying distortion, that's their leading order mode, it goes with 1 over r squared, that they can interact in the far field. And those interactions in the far field allow them to attract each other. Depending upon details of their shape, the particles can attract to form rigid assemblies if they have things like sharp edges. The sharp edges and that faceted end allow them to come very near contact, and then created a steric barrier to reorientation. But the steric barrier was really hinging along the sharp edge and stretching liquid vapor interface. It's not going to fluctuate around this bond. It's quite a deep energy well, and it's a deep energy sort of pit. It has a funny shape. Okay, and that funny shape came from this faceting. Okay. In contrast, if we were a nice curved object like an ellipsoid, we can rock gently around our equilibrium position. Okay, and things like roughness, model roughness, can modulate the interactions in the near field. So I just wanted to allude to work that's just been going on, that's not my work, but that I think is very interesting. And so here's an example of pair interactions caused by particles that are being undulated using external forcing by oscillating a bubble at extremely fast frequencies. So this is work of Valeria Garbin. And in her case, as she undulates at this quasi-static limit, each oscillation makes a monopole. And each monopole then is decaying over distances comparable to to LNR, and she gets very long-range attractive interactions. And in other cases, she gets interactions where she's oscillating at rates where she's exciting capillary waves on the surface, and the interactions are far more complex and they can be repulsive. Okay. And so here's examples where you're putting together the ability of a particle to distort an interface and the ability and forcing of the oscillations. So, so this is the summary of the work on the pair interactions on planar interfaces. And let me stop now and take any questions. And if there are none, I'll hop into just a little bit of the next talk. But if there are some, I'm happy to entertain them.
In the last movie, how was this monopole thing was created?
She's oscillating bubbles at very high frequencies. Yeah, and so I'll show you some structures that she made. That's Valeria Garbin at Imperial.
You said that in the case of the cylindrical particles, it's the edge that's really important. Is it that it's the nonlinearity in the classic equation that matters, or is it just that the boundary is no longer convenient for
It's a great question. You know, we solved, all of that was done using Surface Evolver, which has all the nonlinearities in it. And the distortions are very sharp near the sharp edges of the cylinder, and I can imagine that nonlinearities in the Young-Laplace equation are coming into play. That I would think that we could easily be violating a linear assumption in the steep slope regions adjacent to the corners. I'm not sure that we wouldn't be able to get many of those effects by looking at the Laplacian. But I'd be careful. You have appetite to go on to the next one for a few minutes then? So the question is just looking at curvature. Okay, and we became very interested in this problem because we had this prediction, which is actually sort of backwards, but yeah, it is. When we rederived the results by Stamu, we did that Taylor series expansion, where we said if we want to look at pair interactions, then my particle, I react to the curvature created by Oleg, right? That he makes, that my neighbor can change my height, and I just move with that, and it can change my slope, but I just rotate with that, because I don't have a monopole or a dipole. But that then the curvature field from my neighbor comes to me. And then we thought, well, why not just make a curvature field? Right? And so it's the same abstraction that people make, that you make when you go from Coulomb's law, from pair interactions of charges to Q times E. It's the same abstraction. And so in this case, there's my charge multipole, right? My quadrupolar distortion, the height of my quadrupolar distortion. And this curvature field can be thought of then as the external field. And so we just tried to set up geometries to try to understand the rules. And the first geometry we started with was just a micropost. So we took a micropost that was a couple of hundred microns in diameter, and we pinned the fluid interface at the sharp edge of that micropost. So pin water, and then let it relax out to some ring far away, capillary lengths away, meaning distances over which the interface is already relaxed, to come to that ring. So the ring is of no consequence except the liquid did not spill out. And then we didn't want to look at any fluxes that had to do with evaporation. So on top of that, we gently put in oil. So now we have an air and oil. And then into that, we put particles. Okay? And then we're going to have particles, and they're going to fall onto this curved interface. So this curved interface is a special interface. If we're in the small slope regime, then the shape of the interface near the post is just given by LNR. It's just the logarithm. It's just decaying logarithmically. And so this is a saddle-shaped interface because we saw that that deviatoric curvature, the saddle curvature, was really important in this interaction. And so, we set ourselves up this interface everywhere in the zone of interest. We have the radius of curvature in this direction is equal and opposite to the radius of curvature in that direction. But far away, the curvature is weak, and close to the post, it's strongest. So if you think about that now, in the context of this expression, if we fall on the surface, the energy is going to go down if we move to sites of high curvature. So curvature should be a driving force. Curvature gradients should be driving forces for assembly. Okay. And so this is just reminding you of what we just saw. That was Stamu's story. This is our story. And our micropost, we know the slope at the edge. We just pin it, and we take a picture with the goniometer. And we put the oil, the particles, and then we watch. So this is a top view of a planar disk. And there's our micropost. And so the planar disk is just made of SU8 epoxy resin. And it migrates uphill to the post. So right along radial lines. And we can calculate the energy dissipated. And perhaps more interestingly, we can look at the forces on these objects, and we can find that the forces are on the order of piconewtons. So the energy dissipated over a trajectory, what we do is we just say calculate, integrate the viscous drag, multiplying by a drag coefficient, and we just use Lamb's drag coefficient and an average viscosity. Drag coefficients at fluid interfaces are rich and interesting, and I don't address it here. So we just took an approximate form. But the important point here is that we integrated over our velocity, and we multiplied by some constant of order 1. And we find energy dissipation that looks like this. If we go from our initial curvatures to our final curvatures, and we chose to look at disks always over a certain range of curvature, just so I could graph them all on this graph. Here's our initial position is at some place where our curvature is relatively weak. And then our final position is about 10 radii from contact with the micropost. And we can see that the energy is always going as the distance. The total energy dissipated is just given by the difference in principal curvatures. And if I look at any point along that trajectory of the energy dissipated up to that point, it's a nice line in deviatoric curvature. And so this suggests that this analysis that we did had some merit. And it's also interesting because the changes in the curvature over these trajectories, the distortion, the change in the sort of magnitude of induced distortion made by these particles over these trajectories are just nanometric. So these big objects are moving, and they're changing the distortion, the induced distortion around them by very small amounts. And that's enough to create this energy of interaction. Here are spheres at the same interface. So they're moving uphill and toward the micropost. And again, the energy dissipated over their trajectories is linear. In the disk case, the slopes were comparable to the roughness of the height of roughness on the disks. So we thought of that as a proxy for the amplitude of the quadrupolar mode. In the sphere's case, the slopes are all over the place. The slopes are all over the place. So some have very shallow slopes that are similar to the roughness on the spheres, and some have much steeper slopes. And we think that this is the random contact line pinning. Sometimes the contact line pinning is similar, just along a relatively tight circle to make a small amplitude, and sometimes it's quite large. Okay, so this is probably, I'll go one more slide. So I mentioned this analysis before, but there was a piece that I left out, which was this alignment piece. So I always showed you the energy of interaction of a properly aligned quadrupole on the interface. But the full expression has this argument cosine 2 alpha. And all that is what I was talking about. It's this idea that the particles don't want to ride side saddle, right? We don't want to ride facing the wrong way on the saddle interface, but want to rotate to face quadrupolarize to quadrupolarize. So that torque becomes evident if I look at the cylindrical microparticles. So this is just a cylindrical microparticle snapping onto an interface. It was at this sort of a position with respect to the micropost. It snaps, so there's its torque, and then it migrates toward the post, keeping its orientation fixed. Okay, so there's where I'll stop, and then there'll be a little bit more time for us to go more leisurely in the next piece. So curvature, and in particular this funny piece of the curvature, the piece that has to do with the saddle piece, and this is all in small slopes. Our particles are making small slope distortions, nanometric in height, that are distorting, that are decaying with distances from the particles. They move with an energy dissipation, which is linear in the deviatoric curvature. They have a local torque that keeps them aligned along the principal axes, but that was only evident for the cylindrical microparticle because I was otherwise looking at top views of spheres and disks and you couldn't see it. And so all of them obey this linear dissipation in the deviatoric curvature, and for all of them we recover their expected power law when they're far from contact with the post and they're not having funny drag interactions, hydrodynamic interactions with the wall. So I'll stop there for now. Yeah.
So, questions, please. I have one question. So you spoke about dipoles and quadrupoles in the surface deformation. How far can you go? Right? How complex one can make? Can you make octapole, hexadecapole?
Yeah, yeah. So there are people who've made very beautiful flower shapes, which are just decorating big spheres with little spheres, and then they can lock them in and use them as objects. There's a robotics group that's deliberately making, on a larger scale, fluted objects that are exciting larger scale distortions. So yeah, you can do it. The problem is random roughness. So if nanoscopic distortions matter, then random roughness can give you funny pinning, etc., that can make it more difficult to build up nice regular structures.
So, and when you say random roughness, so what would be the scale?
Nanometric is enough.
Nanometric.
It's enough, yeah. Yeah, so tens of nanometers on the spheres is enough to give us crazy contact line pinning. And then in principle, even smaller scale, if you calculate the excess energies, very small scales, because the surface tension is so large, very small scale roughness for particles that are close enough can play a strong role.
No, let's think it again. Yeah.